Hi everyone. Through this class, we are going to study about the impulse invariant transformation. We know that in digital domain, the processing of infinite samples of impulse response is practically not possible. Therefore, first we design analog filter with transfer function h of s. Then the analog filter with transfer function h of s is transformed into digital filter with transfer function h of z. The popular transformation techniques used for transforming analog filter transfer function h of s to digital filter transfer function h of z are bilinear and impulse invariant transformations. The objective of impulse invariant transformation is to develop an IIR transfer function whose impulse response is the sampled version of the impulse response of the analog filter. The main idea behind this technique is to preserve the frequency response characteristics of the analog filter. It can be stated that the frequency response of digital filter will be identical with the frequency response of the corresponding analog filter if the sampling period t is selected sufficiently small or sampling frequency should be sufficiently high. Let h of t equal to impulse response of analog filter. The Laplace transform of the analog impulse response h of t gives the transfer function of the analog filter. The transfer function of analog filter h of s is Laplace transform of h of t. When h of s has n number of distinct poles, it can be expressed as partial fraction expansion as h of s equal to sigma I equal to 1 to n ai by s plus pi. That is equal to a1 by s plus p1 plus a2 by s plus p2 plus dash dash an by s plus pn. We know that Laplace transform of e raised to minus at u of t is 1 by s plus a. So, on taking Laplace transform of h of s, we get h of t. So, h of t is sigma I equal to 1 to n ai e raised to minus pit u of t. Or it is equal to a1 e raised to minus p1t u of t plus a2 e raised to minus p2t u of t plus dash dash plus an e raised to minus pnt u of t, where this u of t, that is continuous time unit step function, and t the sampling period. Capital T is the sampling period and h of t is the impulse response of analog filter. The impulse response of digital filter is obtained by uniformly sampling the impulse response of analog filter. Therefore, h of n is h of t at t equal to nt, where this capital T is sampling period, or h of n, that is the impulse response of digital filter equal to h of nt. So in this impulse response, by putting small t as nt, we get the impulse response of digital filter. Therefore, h of n is equal to h of nt equal to sigma I equal to 1 to n ai e raised to minus pint u of nt. That is equal to a1 e raised to minus p1 nt u of nt plus a2 e raised to minus p2 nt u of nt plus dash dash plus an e raised to minus pn nt u of nt. On taking z transform of h of n, we get h of z. So h of z is z transform of h of n. And z transform of e raised to minus ant u of nt equal to 1 by 1 minus e raised to minus at z raised to minus 1. Applying this in the expression of h of z is equal to a1 into 1 by 1 minus e raised to minus p1t z raised to minus 1 plus a2 into 1 by 1 minus e raised to minus p2t z raised to minus 1 plus dash 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 plus an into 1 by 1 minus e raised to minus pnt z raised to minus 1. That is equal to sigma I equal to 1 to n ai into 1 by 1 minus e raised to minus pit z raised to minus 1. And we know that h of s equal to sigma I equal to 1 to n ai by s plus pi. That is equal to a1 by s plus p1 plus a2 by s plus p2 plus dash 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 plus an by s plus pn. Comparing the expression of h of s and h of z, we can see that 1 by s plus pi is transformed into 1 by 1 minus e raised to minus pit z raised to minus 1 during impulse invariant transformation. When a discrete time signal is obtained by sampling analog signal, the frequency spectrum of discrete signal will be scaled by a factor 1 by capital T. Due to this fact, the transfer function obtained by impulse invariant method is amplified by a factor of 1 by t for small values of t. If this amplification is undesirable, then the transfer function obtained by impulse invariant transformation can be multiplied by t to obtain magnitude normalized transfer function. Next, we consider the relation between analog and digital filter poles. The analog poles are given by the roots of the term s plus pi for I equal to 1, 2, 3 up to n. The digital poles are given by the roots of the term 1 minus e raised to minus pit z raised to minus 1 for I equal to 1, 2, 3 up to n. Analog poles at s equal to minus pi is transformed into digital pole at z equal to e raised to minus pit during impulse invariant transformation. Therefore, zi equal to e raised to minus pit is now equal to e raised to sit. Thus, si is a point in s-plane. And we know that from this graph, Si equal to sigma I plus j omega I. Substituting this value of Si in the expression of Zi, Zi is now equal to e raised to sigma I plus j omega I into t, that is equal to e raised to sigma it into e raised to j omega it. Since Z is a complex number, we can write it as modulus of Zi angle Zi equal to e raised to sigma it e raised to j omega it, or modulus of Zi equal to e raised to sigma it and angle Zi equal to omega it. Now we can discuss three different cases. First one, when our Si is less than 0. Such points lie on the left side of imaginary axis in S-plane. So the points will lie here. Then if our Si is less than 0, sigma I will be less than 0. That means e raised to sigma t is less than 1, or modulus of Zi is less than 1 in such case. So such points, when they are mapped, they will lie within this unit circle. Then second case is when Si equal to 0, such points lie on this imaginary axis. Then sigma I is 0, therefore modulus of Zi equal to e raised to 0 or 1. So such points in this imaginary axis, they will map into unit circle in Z plane. Then our third case is if Si is greater than 0, such points lie on the right side of this imaginary axis in S plane. Then here we can see that it is e raised to a positive number. So modulus of zi will be greater than 1. So such points, they are mapped outside this unit circle in z plane. And the stability of a filter is related to the location of poles. For a stable analog filter, the poles should lie on the left half of the S plane, and in Z plane, they should lie within this unit circle for stability. Next, we consider the relation between analog and digital frequency in impulse invariant transformation. We know that by impulse invariant transformation, Z equal to e raised to st. And in this equation, put Z as r e raised to j omega. Therefore, Z equal to r e raised to j omega equal to e raised to st. And we know that S equal to sigma plus j omega. So, this is Z equal to e raised to sigma plus j omega into t. And splitting this, it is equal to e raised to sigma t into e raised to j omega t. Now compare this r e raised to j omega with this right hand side. R equal to e raised to sigma t and e raised to j omega equal to e raised to j omega t. Or omega equal to this omega t, where this omega is known as digital frequency. So digital frequency is analog frequency into time period, or analog frequency omega equal to digital frequency divided by t. The mapping of analog to digital frequency is not one-to-one. Since omega, the digital frequency, is unique over the range minus pi to plus pi, the mapping of omega equal to omega t implies that the interval minus pi by t less than or equal to omega less than or equal to pi by t maps into the corresponding values of minus pi less than or equal to omega less than or equal to pi. In general, the interval 2k minus 1 pi by t less than or equal to omega less than or equal to 2k plus 1 pi by t, here k is an integer, maps into the corresponding values of minus pi less than or equal to omega less than or equal to pi. Thus, the mapping from analog frequency omega to digital frequency omega is many to one.